This is lecture number 12 in this course on electric machine design. In today's lecture, we will start with another numerical example. The question is, we are asked to find out the dimensions of the core and window for a 125 kVA 50 Hz single phase oil immersed core type transformer. We are given that the flux density B is 1.23 Tesla, the current density delta is 2.5 ampere per mm square, the window space factor kW is 0.32, and the volts per turn is 17 volts. We have to design a cruciform core where the window height is equal to 3 times the window width. So this is the question and before you solve this question, I want you to pause this video and try to solve this question on your own, and if you're not able to solve it, you can see the remaining part of the video. So let's start. We know that the EMF equation for the transformer, and from the EMF equation we can calculate the flux, which is given by this. So if you put in the values, you will find out that phi m comes out to be 0.0765 Weber, and since you know bm, this is bm here, from bm and phi m you can calculate area, iron area, bm by phi m by bm, which is the net iron area. AI is phi m by bm, and if you substitute the values, it comes out to be 0.062 meters square. We also know that for a cruciform core, the net iron area is equal to 0.56 times d square, where d is the diameter of the circumscribing circle. So d for this case can be found out, and it is equal to 0.332 meters. Now for the cruciform core, you know that the cruciform core is like this. Yeah, it is like this, and this part is A and this part is B. If you look at the derivation for the values for the cruciform core, we find out that this A is 0.85 times D, which is the standard for cruciform core. So this comes out to be 0.282 meters. So this A is the width of the largest stamping, and from the same expression we can find out B, the smallest stamping, and that is 0.53 times D, and if you put in the value, it is 1.75 meters. These equations are standard for cruciform cores. If you have any doubts about this, you can refer to the book and see how these expressions are actually derived. Now, the height of the yoke HY is about 1 to 1.5 times A. So we can, if we assume the value to be 1 times A, we can simply say that the height of the yoke is the width of the largest stamping, Now we know all of these values, so what we can do, we can then proceed to calculate the output kVA, which is 2.22 F delta AI BM AW kW into 10 to the power minus 3. The only thing that you'll have to be careful about is this value delta. Just fix the units into meter square, right? So we have Q is given to us. We are interested in calculating the window area AW here. So window area is found out to be 125 into 10 to the power 3 divided by 6.77 into 10 to the power 6. So that is 0.0184 meter square. Now this is the area of the window, and we are told in the question that the window height should be equal to 3 times the window width. The window height should be equal to 3 times the window width, and we also know that the area of the window is equal to height of the window times width of the window. So if you substitute these values, you get that the width of the window can be found out to be 0.078 meter, and the height of the window is 3 times this value, that is 0.234 meters. Then when you get all of these values, the overall height of the transformer is given by this comes out to be 0.79 meters. Then if you find out the overall width of the transformer W, it is WW plus D plus A, and this comes out to be 0.688 meters. So with this we find out the 3 important parameters, that is H, W and A. These have all been computed, and this is what was required. And with this we come to the end of this question. Now I would encourage you to solve more questions. So to get a better understanding of the subject, you can refer to the book for more such questions, and I would also encourage you to solve some unsolved problems given at the end of the chapter, so that will also be of great benefit to you. Now moving ahead, we will now talk about resistance calculation. And if you ask why resistance is needed to be calculated before the transformer is designed, this is because we want to estimate the copper losses in the HV and LV windings of the windings, and based on these losses we will find out the temperature rise, the cooling system to be designed, etc. So this is all the result of the calculation of the resistance. Fine. So what happens to calculate this resistance? We first need to find out the area of cross section of the conductor of the HV and the LV windings, and from these we can calculate the mean length of the conductor, mean length of LV and HV. Okay, so if we go to the definition of resistance, we know that the resistance of the primary winding per phase, it is equal to, it is rho now rho is the resistivity, LMT is the mean length of turn, AP is the cross section of the primary conductor, and TP is the number of turns. On the same analogy, for the secondary winding, RS is rho LMT by AS into TS, right? As a side point, LMT for the primary is pi times the mean dia of primary. This is the mean length of turn of the primary, and mean length of turn for the secondary is pi times mean dia of secondary. Okay, so based on these values we can find out the resistance Rp and Rs, and some additional information. At 60 degrees, the copper resistivity is about 2.1 into 10 to the power minus 6 ohm centimeter. Okay, so this gives you an idea of how low the resistivity of copper is, right? So you can get an idea, and you can call this as LMTP and MTS, like this. So when you refer the resistance to the primary side, the total resistance per phase referred to the primary side, this is from your knowledge of machines, R1 is equal to Rp, which is the primary resistance, plus number of turns of primary by number of turns of secondary squared Rs. You are all aware of this equation. This is the turns ratio, and this gives you the total resistance of the transformer when referred to the primary side. Next, we calculate reactance Now reactance, we should know that it comes from flux. So there are three types of flux associated with the transformer. You can have useful flux, you have leakage flux, right? No, sorry, not three but two types of flux are associated with the. So this useful flux is responsible for the electromagnetic energy transfer, and this is the path of this flux is the core only. The leakage flux, on the other hand, it is responsible for imparting inductance to the windings. Because it is not part of the main flux and it is the part of the flux that is outside the core. So this is not part of the main core. So this leakage flux depends on the geometrical configuration of the coils and the neighboring iron masses. So this is all about the leakage flux. So based on these two fluxes, we have the reactances and the leakage reactance is 2 pi Fl times inductance where this is 2 pi Fl times flux linkage over current this is 0.1. The flux linkage flux into number of turns and this flux is also the mmf or the ampere turns. It is equal to the ampere turns into the permeance. We have already derived this expression, that is lambda, and the permeance lambda is equal to 1 over reactance, which is equal to A times mu naught mu r by L. Now some key points to note here is that this small a is the area over which the flux is established. L is the length of flux path, right? So these are all the basic definitions. Now if you have xp and xs as the leakage reactances of the primary and the secondary, then the total reactance of the transformer referred to the primary is given by xp, capital XP, and that is xp plus xs dash, where xp is known to us and xp xs dash you get by taking this ratio, number of turns squared xs. And if you want to get the reactance referred to the secondary side, it's going to be xs plus xp dash, which is xp plus the inverse ratio whole squared times xp. So one other thing that you must keep in mind is that this estimation of this leakage flux or reactance is always difficult, because this involves the calculation over a complex geometry. So depending on the depending on the application and the critical nature of the use, some appropriate expressions have to be used so that we can get an appropriate estimate. Of course, whenever you make some approximations, you always check those approximations, and you evaluate those expressions with some test data. But I won't go into the details about these approximations. I leave that as an assignment to you, so you can see the leakage reactance of core type transformers with LV, with concentric LV and HV of equal height and length. You can see this derivation from the book, and just the derivation, you don't need to do anything else. Just see the derivation and see how the expression is evaluated. Fine. And after this, I would want you to see this is the assignment. You don't need to submit this assignment, but just go through these two things. One is the assignment, you have to see the calculation for the leakage reactance, and number two, you have to see the flow chart for overall design of the transformer. This is number two. I would want you to go through this flow chart and see the exact design process, about how this transformer design process is actually carried out. Fine. And of course, I'll repeat, I would want you to go through some numericals. And with this, we come to the end of this lecture. In the next lecture, we will talk about some operating characteristics of transformers, and we will talk about no load current and some calculation of some